Okay, maybe we can start. So the first job of today is going to be explaining the topology of the space of hypersurfaces, which is really crucial because the idea of minimax theory or of Morse theory is that you need to understand the topology of the underlying space so that one can construct sufficiently many critical points. So last time I talked briefly about flat chains, and then I defined the space Pk, which was the space of k-dimensional polyhedral chains modulo 2 in some R n, where n is big. So the definition of what a flat chain is simply so the space, I call it Ck of Z2, space of flat chains, k-dimensional flat chains modulo 2 in Rn is just the completion as a metric space of the space of polyhedral chains with respect to the flat topology. So this is the definition. So it's a metric space. Basically, a flat chain is something that can be approximated by polyhedral chains in the flat topology. And then inside that space, there's another space which we call Ik of Z2, and this is just the space of chains T such that both the mass of T and the mass of the boundary of T are finite. So this is the space of rectifiable chains. So in the space of flat chains, there's a natural notion of boundary, just coming from the definition of boundary of a polyhedral chain. There's a natural notion also of mass, which basically measures the k-dimensional volume of your chain. There's also a natural notion of what the support is in the space of flat chains. So one basic result about flat chains is the compactness theorem. Which is due to Federer and Fleming, essentially. Says that if you give me K contained in Rn, if this is a compact set, then I can look at the following space of chains. So I look at all chains T, rectifiable chains, such that the mass of T plus the mass of the boundary of T is less than or equal to C, where C is a given constant, and such that the support of T is contained in the compact set K, then this space is compact in the flat topology. For every constancy. Okay, so the space of flat chains that has both the mass and the mass of the boundary uniformly bounded from above is compact in the flat topology. So this is very useful, for instance, if you're trying to solve a problem of minimization like the Plato's problem. So if you give me, say, some boundary, say gamma in Rn, then I can look at I can consider all chains such that the boundary of the chain is equal to gamma, and then I can minimize, so you can take the infimum of the mass of all chains T such that the boundary of T is equal to gamma. And basically the compactness theorem will say that compactness theorem combined with the fact that the mass is lower semi-continuous with respect to the flat topology tells you that automatically there's going to be a chain, special chain sigma, such that the mass of sigma is equal to this infimum. Because you take a minimizing sequence of chains, both the mass and the mass of the boundary are going to be uniformly bounded, so you can take a limit. You can take a limit in the flat topology of a subsequence, and lower semi-continuity of mass will say that the mass of the limit is less than or equal to the lim inf of the masses. So in particular, if it's strictly small, it would be even better. So the Plateau problem can be solved by using this theorem. Of course, after one constructs such a chain, one has to prove that the chain is smooth or regular in some sense. So there's regularity work. So the problem with minimax is that lower semi-continuity of mass won't be enough, right? Because of the phenomenon of cancellation of mass. So let me just illustrate the cancellation of mass is the fact that, so suppose you give me, for instance, say my chains are just two disks with distance epsilon, so say d1 and d2, then as epsilon goes to 0, if I consider the chain that's just d1 plus d2, as epsilon goes to 0, this actually converges in the flat topology to the zero chain, because when the two disks overlap, they're going to have multiplicity 2, so it cancels out. Okay. So although the masses, say, maybe they're equal to 2 pi or something like that, the limit has 0 mass, and then you lost everything. So we're going to solve that problem by also considering the notion of varifold. But before getting there, let me explain the topology of the space of hypersurfaces. Okay, so the space of hyper cycles. So what is this? So here I'm going to imagine that I have a compact manifold of dimension n plus 1. So you'll always denote the dimension of the ambient space by n plus 1. So this is a compact Riemannian manifold. By the theorem of Nash, we know that this can be isometrically embedded in some Euclidean space. So let's assume that we have such a isometric embedded. So this is isometrically embedded. And I am assuming that M is compact. So then I can denote by I, say n plus 1 mz2. Now, this is going to be the space of all n plus 1 dimensional chains that have support contained in M. Okay, so this is the space of all T's in I n plus 1 z2 such that the support of T is contained in M. So this is going to be my space of top dimensional chains. So this space is actually a group. So one can think of an element here as just some region in my manifold. So for instance, if I take two top dimensional chains, let's say some region U1 like that inside my manifold, and I have another region U2, another top dimensional chain, I'm thinking about the open set here, then if I consider the sum of them, what's going to happen is that the overlapping region will cancel out because it's going to appear with multiplicity 2. So the sum is just this guy here. It's going to be U1 plus U2. Okay, so that's the space of top dimensional chains. And then we consider the space of cycles, which let me denote by Z hat here. I want to consider the space of hypersurfaces, so codimension 1. So this is going to be the space of T's, which are they are n-dimensional chains with support in M, and they have the property that the boundary of T is equal to 0. Okay, so the space of all n-dimensional chains with support contained in the manifold and such that the boundary is equal to 0. So this is the space of cycles. But actually it's more convenient to consider the following subspace, which I dropped the hat here. This is going to be the space of all T's such that T is the boundary of U, where U is a top dimensional chain. Okay, so I consider the space of all boundaries of top dimensional chains. And that's my space of cycles. So just one comment that in Z hat, not necessarily T is the boundary of something. For instance, if your manifold is like a torus, if you take T to be this curve, this is a cycle because it has boundary 0, but it's not the boundary of anything. Right? So this guy would be an element of Z hat, but not an element of Z. So the idea is that Z is actually in the flat topology, this is going to be the connected component of Z hat that contains a 0 cycle. Zero cycle. I'm going to consider this connected component. Okay, so then the proposition, which I'll try to explain the proof here, says that this space of cycles is what we call weakly homotopically equivalent to the infinite dimensional projective space. And this holds true for in any dimension for every manifold M. Okay? So what's the idea here? So we're going to consider a map from RP infinity to the space of cycles, and then we're going to prove that that map induces isomorphisms in every homotop group. So this is the definition of what weakly homotopically equivalent is. So consider the following map. So choose a Morse function. Choose a Morse function. Say F from M to R. Let's normalize things so that the image is the interval 0, 1 always. So I already described here the one parameter sweep out given by level sets of F. Okay, but now I'm going to explain why there are actually k parameter sweep outs for every k. So now we consider the following map that I will call phi hat. So this is a map from RP infinity to the space of cycles. Given by the following formulas. So I take phi hat. If you give me a point in RP infinity, it's going to have projective coordinates like this. At some point, these numbers will be equal to 0. So this is a point in RP infinity. So my definition is going to be the following thing. So I'm going to consider the set of points in the manifold such that when I consider the expression a0 plus a1 f of x plus so on, ak f of x to the power k, this is less than or equal to 0. So I build a polynomial with coefficients ak in terms of the most function f. So this is a function in my manifold. I look at the region where the function is negative and I take the boundary. Okay? So because this is a boundary, it's going to immediately lie in my space of cycles. Okay, so this is the definition. So let me explain better this. So phi hat is continuous in the flat topology. So what's going on here is that, if you give me a polynomial with coefficients a0 to ak, the polynomial in the real line, it's going to have a bunch of roots. So some roots will appear with multiplicity, with even multiplicity, and those you forget. You look at the roots with odd multiplicity. And then basically, if this is the picture of my manifold M, if I have that the roots are maybe, if these guys are the odd multiplicity roots of the polynomial a0 plus a1t plus ak t to the k. So this is a polynomial, has a bunch of roots. You take those with odd multiplicity. Then basically the cycle is just going to be the sum of the level sets corresponding to those roots. Okay? So the image of a point here is always a union of level sets of f. And the point is that if I consider given a polynomial in the real line, if I consider the roots with odd multiplicity, then this is a cycle, it's a zero cycle, and that zero cycle is continuous in the flat topology. For instance, take the polynomial maybe degree 3, which does something like this. So the roots are going to be these three guys here. And then maybe you can push the polynomial down so that eventually it's going to do this. But then when it does that, what happens is that this root now has multiplicity 2. So these roots are coming together. And because I'm taking coefficients modulo 2, basically they will cancel out. Okay, so when I get this, I don't count the root here, I only count this guy here. And then you can just continue. Okay, so these points are zero cycle modulo 2, and they depend continuously on the polynomial. So that's the reason why phi hat is continuous in the flat topology. Okay. Erase this. the claim is that the phi hat induces isomorphisms in every homotop group. So if this is true, we say that phi hat is a weak homotop equivalence. So I'm going to explain why. Well, first of all, recall that pi 1 of Rp infinity, say based at the sum point. Suppose I take the point, the number 1, a0 equals 1, so this is a point in Rp infinity. So one has to recall that pi 1 of Rp infinity is z2, and pi k of Rp infinity is equal to 0 for every k greater than or equal to 2. So these are the homotop groups of Rp infinity. And the way you prove this is by considering the infinite dimensional sphere, and then there's a natural projection from the infinite dimensional sphere to infinite dimensional projective space. So the proof just uses the fact that the infinite dimensional sphere is contractible. I'm not going to prove that, just accept this. So the idea is that if I take a, so if I consider pi 1, I'm looking at paths in Rp infinity, say connecting some base point x naught. Then when you lift the path to the infinite dimensional sphere, either the lift is going to be open, it's going to maybe go from x naught to minus x naught, or maybe it closes up. So if the lift is open, this means that this path is non-trivial homotopically. And if it's closed, because the sphere is contractible, the loop downstairs has to be trivial. Okay, so that's how you detect whether a loop is trivial or not. You just look at the lift and try to see whether the lift is open or closed. And if k is greater than or equal to 2, then it's easy, because then the sphere of dimension k is simply connected. So given a map from Sk to Rp infinity, you can always lift to the infinite dimensional sphere, and then the infinite dimensional sphere is contractible. So that's how one does it for Rp infinity. So I'm going to explain now why the same kind of thing exists in the context of cycles. So the idea is that first, I'm going to use what we call the Constancy Theorem. From GMT. What it says is that if I have a cycle, okay, so if I have a chain, top dimensional chain in my manifold, so think of this as some region in the manifold. Then if the boundary is equal to 0, there are only two possibilities. Either T is equal to the whole manifold, or T is equal to 0. Okay, so the only two regions in my manifold with boundary equal to 0 are the trivial guy, or the whole manifold. So this is called the Constancy Theorem. So what this implies is that if I consider my boundary operator, which goes from the space of top dimensional chains, space of cycles, so this boundary operator is going to be a 2-cover, right? Because if I take a cycle T, so this cycle is the boundary of some region U, but it's also the boundary of M minus U, and U and M minus U are the only possibilities because of the Constancy Theorem. Okay, so So the boundary operator is a 2 cover, so the boundary operator is just like the projection. And then one can also prove that the space of top dimensional chains is contractible. So the space of top dimensional chains is contractible. So just like the infinite dimensional sphere. So the proof is simple. You consider, if you give me a region U, I consider the following deformation. HT of U is going to be the intersection of U with a set of points where f, my most function f, is less than or equal to t. So this is for t between 0 and 1. Then by definition, you see that H1 is just the identity, and H0 is just a constant guy equal to 0. So I showed that the identity map is homotopic to a constant map, so it's contractible space. Okay, so that's basically the proof. You know, you have a 2 cover. The covering space is contractible, so you compute the homotop groups of the space of cycles, just like you did it for RP infinity. So pi 1 of the space of cycles, say based at the 0 cycle, is going to be equal to Z2, and pi k space of cycles is going to be 0 for every k greater than or equal to 2. Okay? So how does one detect whether a loop is trivial or not? So the remark is that if you give me a map, say sigma, from the interval 0, 1 to the space of cycles, suppose that sigma of 0 equals 0 and sigma of 1 is also 0. Okay, so this is a loop. Well, because of this picture, this loop is going to be contractible if and only if, when I lift it to the space of chains, the lift is closed, just like in RP infinity. So what you do is, this guy is to be homotopically trivial, if and only if the lift, say sigma tilde, to the space of chains satisfying such that sigma tilde of 0 is equal, say, to the 0 chain, satisfies sigma tilde of 1. Maybe I should say homotopically non-trivial. It's better if sigma tilde of 1 is the whole manifold. So what is going on? This guy is supposedly a 1-parameter sweep out of my manifold. So I want to know if this is really a sweep out, well, meaning that if it's a non-trivial family. So what I do is, as I evolve my cycles, so I keep track of the region the cycle bounds. So if it's a sweep out, what's going to happen is that if you start with the 0 region, then if it's a sweep out, you have to end with the whole manifold. Okay. So when that happens, you say that this is a sweep out. So in particular, my example yesterday, if I take sigma of t to be just the set of points, the boundary of the set of points where f is less than or equal to t. So just looking at the level sets of my most function, this guy is homotopically non-trivial. Right? Because when I look at the region it bounds, it starts with a trivial guy and ends with a whole manifold. So the family given by level sets of a most function generates the fundamental group of the space of cycles. Okay, so this is basically a sketch of the proof that this map is going to be a weak homotopic equivalence. So one remark. So what's the question, sir? Right, so what I showed here was that the homotop groups are the same, but then it's easy to check that when I look at my map phi hat, which goes from RP infinity to the space of cycles, if I take non-trivial loop in RP infinity, it is non-trivial, then the image of phi hat is also going to be non-trivial in Zn. So phi hat sends a generator of pi 1 of RP infinity into a generator of pi 1 of Zn. And for the higher homotop groups, you don't need to care because both are trivial. So phi hat really induces isomorphisms in every homotop group. That particular map that I wrote does this. Yeah. Right, because if you, let me maybe be more explicit. If I take phi hat and I consider the image of the point, say, t, and maybe here 1, this is going to be the boundary of the set of points where, say, t plus f is less than or equal to 0. So you're basically getting the level sets of f. Yes? What's the question? I chose any f. Yeah, yeah. Oh, you mean a proof that doesn't use f? Well, yeah. I mean, there are other ways of computing the homotop groups of this space, actually. So there's a, maybe I should mention, there's a beautiful formula of Almgren. This is called Almgren's isomorphism. It's actually his PhD thesis, 1960. That he shows that it's a very general formula. If I take the space of L-dimensional chains in some manifold, and if I compute pi k of this, maybe based on the 0 cycle, say, this is canonically isomorphic to k plus L dimensional homology of M. So this is the formula. So in particular, if you have codimension 1, so this is going to imply that pi 1 of Zn mn plus 1. This is going to be the top dimensional homology of M, which is equal to Z2. And of course, pi k is going to be 0 because there is no homology in higher dimensions. So, yeah, so there's a more general formula behind it. Yeah. So the proof of that's not so, I mean, the intuition is clear, but it's kind of technical. So in the particular case that I have in mind here, one can do a simple proof like that, as I explained. Okay, so it's very good, right? Because it's telling me that the space of hypersurfaces has very interesting topology. So it's like an RP infinity. In particular, I have an RPK for every k, so this is telling me that I have non-trivial families of surfaces parametrized by RPK. So you can think that, well, I take this family, I do minimax for families that are homotopic to it, so I get a minimal surface for every k, then I get infinitely many minimal surfaces. Well, you have to be careful because there's the phenomenon of multiplicity that minimal surfaces can come with some integer number, and you could be producing the same surface with high and high multiplicity. This doesn't give a proof, but it suggests that it should be true. So one remark is that actually this formula is the same for, it's true also for integer coefficients. So if you do the calculation for, if I take cycles with integer coefficients and you compute the homotop groups, you see that if M is oriented, you see that pi 1 is going to be Z, and the high dimensional guys are going to be 0. So this is really weakly homotopically equivalent to a circle, which is not interesting. Right? So if I take integer coefficients, the space is very simple. I don't have enough topology to hope to solve the Gauss conjecture. Okay, if M is oriented. So the moral of the story here is that Z2 coefficients is really a crucial thing. All right, so we have interest in topology. We can hope to do a minimax. But the problem is that you could have laws of mass. So that's why one needs to be a bit more careful. And the way Almgren solved this problem was by introducing the notion of varifold. So Almgren wrote this monograph in 1965 where he introduced this minimax theory, and in that monograph he introduced the notion of varifold in order to solve this problem. So maybe let me say a few things about varifolds. I hope we have enough time. So let's see how much time I have. Okay, so a varifold is a measure. So first on the Grassmannian. So I'm going to consider my big Euclidean space, and then I'm going to denote by G n over n. This is going to be Rn cross G little n n. So this guy is the space of n-dimensional vector subspaces in Rn. And of course, the first variable is just the base point. So this is really the Grassmannian. The n-dimensional Grassmannian of Rn. It's the space of all affine n-dimensional vector subspaces. So then the definition is that you say a varifold non-varifold. V is just a random measure, non-negative. Radon measure. On the Grassmannian. So in my notation is I denote, I say the V belongs to Vn. So it's a measure on the Grassmannian. So what's the intuition here? Well, the intuition is that if you give me a submanifold of dimension n, that induces a varifold. So example, if you give me a C1 compact embedded submanifold of dimension n in my big Euclidean space, you can even give me multiplicity, which is a function theta from sigma to the positive integers. So then I define the varifold sigma theta. So random measure means you are a continuous functional on the space of continuous functions here. So if you give me a function f on the Grassmannian, my varifold sigma theta returns the integral over sigma. So this is a function on the Grassmannian, so I can evaluate it at the point x tx sigma, because sigma has tangent spaces. And then I can multiply this by the multiplicity at x. And then I can integrate with respect to the natural measure on sigma, which is the Hausdorff measure. So this is the definition for every function f continuous with compact support on the Grassmannian. Okay? So whenever you have something that has tangent spaces almost everywhere, like a rectifiable set, for instance, one can define a varifold. Okay, so what can I do with the varifold? First, the varifold V induces a random measure. It's a measure on the Grassmannian, but it induces a measure on the base space, which I denote by this bracket V on Rn. Well, what is the definition? It's the natural thing. So this is going to act on a function, on a continuous function on the base. So by definition, I say that this is going to be V evaluated at f composed with pi, where pi is the natural projection. It's just the natural projection. Okay, and then I have the notion of mass, which basically is the little n dimensional volume of my varifold. It's just the mass of a varifold V. It's just the total measure. So it's going to be this guy evaluated at the whole Rn. Okay, so this is the mass. So the definition of varifold is really natural from the point of view of the first variation formula. So let me explain first variation. So in order to explain what the first variation formula is, I need to first introduce the notion of push forward. So suppose that you have a varifold V, and suppose that one has a map C. Let's say the map goes from Rn to Rn. Then I can define the image of V under psi. And this is going to be my push forward. So the formula is basically the formula that you get coming from the change of variables formula. So what you do is this varifold psi. Maybe I should use the language of measures. It's better. So this is going to be a measure on the Grassmannian. So if I evaluate this measure on some function f, I get the following kind of expression. So basically, I'm integrating f on the Grassmannian. So it's a function of, say, a point in the space. So say I integrate this with respect to the push forward measure. So by definition, this is going to be the integral of f x, and then here I have d psi x evaluated at pi. And then I have to correct by the Jacobian of psi x pi dv x pi. Okay, so if you know the varifold v and the map c, you get the push forward varifold. So this is really the generalization of the change of variables. So this guy is the Jacobian. J psi x pi is the Jacobian determinant of the linear map derivative of psi restricted to the space pi. So this is the definition of push forwards, like the image of v under psi. So now, if you give me a vector field x, so if you give me x, some vector field in Rn, I can consider its flow psi t. So basically, this is defined by the following ODE. Standard thing, right? So given a vector field, I consider the one parameter flow generated by it, and then I do the following calculation. So I consider the push forward under psi t of my varifold v. I take the total measure of that, so the mass, take the mass of that, and I differentiate this with respect to t. So what this gives me, this is the first variation formula, is the integral of the divergence of x with respect to pi. So x is a vector field in Rn. If you give me an element of the Grassmannian, so this is a vector subspace, at some point I can compute this divergence. So this is naturally a function of the Grassmannian. So I can integrate with respect to the varifold v. So this is the first variation formula. What I think of this as, this guy is just the sum of EI, where EI is an orthonormal basis of pi. What I think of pi as a vector space based at some point x. Okay, so that's the I guess the motivation for defining a variable, that when you compute the first variation formula, you get something a function which is naturally a function on the Grassmannian. So the consequence is that is the following thing, that if I have the space of variables are measures. So I have the weak topology. Just say that a sequence of varifolds converges to a varifold V if, by definition, Vi of f converges to V of f for every f. This is just the weak topology. Observation is that now the mass is continuous with respect to the weak topology. Okay, there is no loss of mass anymore because it's just measures. And now if you look at this expression here, right, basically this is V evaluated at the divergence formula. So if Vi converges to V in the weak topology, then let me introduce a notation for this. So my notation is delta V of x. So if Vi converges to V in the weak topology, then the first variation of Vi with respect to any fixed vector field converges to the first variation of V. Okay, so the first variations converge also in the weak topology. Okay, this is what a varifold is. And then we are interested in minimal surfaces, right? So minimal surfaces are critical points of the area functional. So there's a corresponding notion at the level of varifolds. It's what we call stationary varifold. So one definition. First you say that, so my notation is that V belongs to Vn of M. Remember that I'm always assuming that M is something that is isometrically embedded in the big Euclidean space. So this is just a varifold whose support is contained in M. Okay? So if V is a varifold with, if I look at the measure bracket V, the support is contained in M. So definition, you say that a varifold in my manifold M is called stationary in M if the first variation is equal to 0 for every x that is tangential to M. Okay, so the first derivative of the area is equal to 0 for every variation that preserves my manifold. When this is true, then you say that V is stationary. Of course, I mean, some examples. Well, a minimal surface satisfies that, right? So if sigma contained in M is a minimal hypersurface, then this is a stationary varifold. But stationary varifolds are still very far from being minimal surfaces. For instance, if you give me 3 planes, let's see if I can draw the picture. 3 half planes with 120-degree angles. This is also stationary. You can check from the first variation formula. So this is, of course, very far from being a minimal surface. And even if it is a minimal surface, the other example is that even if you know that the support is a minimal hypersurface, it could happen that the multiplicity could be any real number. So if you give me any number alpha positive, and sigma is minimal, this is also stationary. Okay, which is very bad, because if I do minimax and I can get something like alpha times sigma where I do not control alpha, basically I have no information about the area of sigma. So this is the problem of non-integer multiplicities. But fortunately, this is not going to happen. The minimax theory will not produce something like this or like that. It's going to always produce a smooth minimal hypersurface with integer densities. So it's a good thing. So are there any questions? The most function? So triple junctions one can exclude by the fact that, for instance, if you take 3 half lines with 120 degrees, this is stationary, but it's not a cycle. Not cycle modulo 2, because if I compute the boundary, the origin is going to appear with multiplicity, well, 3, which is equivalent to 1 modulo 2, so it's not a cycle. But they could appear with multiplicity 2, and that is a cycle. Okay. So a triple junction with multiplicity 2 is in principle, is a perfectly fine object that we have to rule out. Yeah, if the map is Lipschitz, it's enough. Yeah. Yeah, I mean, everything that we care about is inside M, so you can do all these definitions by taking M instead if you want. So you can talk about Grossmanian of M intrinsically. Oh, you mean the manifold? No, in our case, it's going to be smooth. Yeah. In our case, it's... Well, these notions make sense for general M. I mean, it's just that in this setting we're talking about minimal hypersurfaces and smooth Riemannian manifold, so I don't really need to go into that. Yeah, but the notions definitely make sense. Okay, I have half an hour, I guess. So what I'd like to do now is maybe of course I don't have enough time to go into the proofs, but I'd like to explain the steps in minimax theory. First, just one observation that, well, this is one of the reasons the theory is not so easy, okay? It's because in order for everything to work, we need to actually work with both concepts, which are, of course, different. The flat chains are important because they give us topology. They give us this RP infinity structure that we cannot hope to have with varifolds, right? Because for varifolds, for instance, the boundary map is not defined. So flat chains give us the topology, and varifolds give us the hope of producing something non-trivial in the end. So you really have to work with both things. And if you look at the original monograph of Almgren, it was even very complicated because it considers the space of pairs. The first variable is a chain, the second variable is a varifold. Fortunately, Pitts has improved on that. Anyway, one more remark that I won't prove is that a flat chain modulo 2 always induces a varifold. So it's n-dimensional. invariable, which I denote by absolute value of t. So if I say that f, the space of measures is metrizable, so you can choose a metric in the sense of metric spaces. So let's call it f. So this is the varifold distance, which is compatible with the weak topology. So we have seen that in the space of chains, there are these two topologies. One very strong, called the mass. Right? So we have the mass metric. It's very strong topology and kind of weird in some sense. And then we have the much more natural one. It's called the flat topology. But the area is not continuous with respect to the flat metric. So there's actually an intermediate metric that one can use. It's called the F metric, which is defined in the following way. So if you give me, let me say that now we are considering cycles, my manifold. Then the F metric between these two cycles is just the sum between the flat distance and the varifold distance between the corresponding varifolds. Okay, so this is called the F metric, and it's something in between here, in between the mass and the flat metric. So let me illustrate this different of the different topologies. So for the flat metric, actually, it's very weak, because if you have a cycle, say maybe S, in order for a cycle to be close to S, it's enough that the volume of the region in between the two cycles is very, very small. So I can have something that looks like this. Maybe there is a hair like that. But as long as the volume of the region in between these two guys is very, very small, they are close in the flat topology. So this is flat. Well, for two cycles to be close in the F metric, they have to be close in the flat distance, but they also have to be somehow close as varifolds. And notice that varifolds somehow keep track of the tangent spaces. So the intuition is that maybe two cycles like this, they are close in the F metric. But they are still very far away from each other in the mass metric, right? Because this was the example I explained last time. If there's no overlap, the mass of the difference would be the sum of the masses. So in order for two cycles to be closed in the mass metric, something like this has to be true. If this is S, then T has to differ by just a small amount. Okay, so it's a very strong topology. Anyway, in applications, the interesting applications that we have found, starting with the Wilmore conjecture, the natural families that come in are actually continuous in the flat topology. Okay, so, and then there's the issue that the mass is not continuous. So it's important to have some technical machinery, which I won't explain here, that allows you to approximate some family that is continuous in the flat topology by something that is continuous in the F metric or even in the mass metric. So such machinery exists, is what we call interpolation. But I won't explain that here. So let's maybe not worry so much about the topologies, because one has to be careful here. But anyway, how the question, the rest of this lecture, I'd like to explain the one parameter minimax. Or if you want, I want to answer the question how to construct one minimal hypersurface. Okay, so the idea is that you have to have sweep outs, and now we do, right? Because pi1 of the space of cycles is Z2. So you consider a map phi from the interval 0, 1 to space of cycles. You say the phi belongs to, say, let's call it maybe pi1, because this is the class of one parameter sweep outs. If, well, first, phi is continuous in the flat topology. Secondly, oh, maybe I should say that the boundary conditions are the phi of 0 is 0 and phi of 1 is 0. So they start and end at the 0 cycle. So it's continuous in the flat topology. It has to be non-trivial, which means that the lift, so there is lift phi tilde. Maybe I should say not phi tilde. We should say U to the space of chains, such that the lift means that the boundary of U of t is equal to phi of t. And for this to be non-trivial, the lift, if I start with the 0 region, I have to end with the whole manifold. So this is the non-triviality assumption. And technically, maybe I should just say that there's a third technical condition. It's called the no concentration of mass. Which means that if I take the sup for every t in the interval 0, 1, and every point in the manifold of the mass of the intersection of phi of t with the ball of radius r centered at p, and I take the limit of this as r goes to 0, this is 0. So this is saying that I cannot have, say, mass equal to 1 in smaller and smaller balls. Okay. So the reason why we need these conditions, because we have to do these approximations. We have to go from the flat to F metric, or even to the mass norm. So it's a condition that originated in our work on the Wilmer problem. So I won't try to go into detail here, but there is a condition. So then you do your minimax. So the minimax number, W, well, it's minimax. So what you do is for every map phi in this class, this is pi1 is the homotop class, I maximize the mass and then I minimize this over all maps. So this is my minimax number, which is sometimes called the width of M. So this is the least amount of area that you need to be able to sweep out your manifold. Then, like in Birkhoff's argument, the first thing we have to do is to prove that this number is positive. And in order, I would like to explain this. So in order to see that this number is positive, we need the isoparametric inequality of Federer and Fleming. So the statement is the following. It says that there exist two constants, say nu and b positive, depending on the manifold. Such that for every cycle, for every t in Zn, so this means, of course, boundary of t is equal to 0. So if the mass of t is smaller than nu, I can find a top dimensional chain U. So I can find a filling, if you want. So boundary of U equals T with mass of U estimated by the mass of T, by the constant B times mass of T, power n over n plus 1. I think it's the opposite, n plus 1. Okay, so this is saying that if my cycle has very small mass, I can find a filling with very small volume. This is the isoparametric inequality. So I claim that this implies the fact that this number is strictly positive. And the reason is the following. Suppose that this number is very small. Maybe let's suppose this number is smaller than, well, let me put an epsilon here, where epsilon is very small. I'm going to get a contradiction. So the idea now is that I can find a minimizing sequence, right? So if W is less than or equal to epsilon, this means that there exists a map phi in my class such that the sup of the masses is less than or equal to 2 times epsilon. So if epsilon is very small, I can apply the Federer-Fleming isoparametric inequality to every phi of t. So Federer-Fleming is going to say that there exists a chain U of t such that the boundary of U of t is equal to phi of t, and such that the mass of U of t is going to be bounded by, well, b times the mass of phi of t, which in this case is at most 2 times epsilon. Okay, so for every phi of t, I have this region U of t. And the point is that because the mass is very small, actually U of t is unique. Remember that there are only 2 choices, U of t and the complement of U of t. So the volume of the whole manifold is less than or equal to the volume of U of t plus the volume of the complement. So this implies that the volume of the complement is at least the volume of M minus the volume of U of t, but then by my estimate, this is something like this, very small number. So if U of t is very small, then the complement, of course, is very, very large. So this small guy is unique. Okay? The fact that it's unique implies that if I consider my map U from 0, 0, 1 to the space of chains, this is going to be continuous. In flat topology. But notice that U of 0 is equal to 0 because phi of 0 is 0, so the only small guy that has its boundary is the trivial chain, and the same holds for U of 1. Right? Because phi of 1 is 0, therefore by uniqueness, U of 1 has to be 0 also. So this is a contradiction. Because I found a lift that is closed, so it cannot be. Okay? So this proves that W is positive. Okay, so then this is good. So what are the steps in trying to do this? So let me introduce some notions. First, we choose a minimizing sequence. Minimizing sequence is just a family of phi i's in my class of sweep outs such that the sup of the masses of phi I of t, as t goes from 0 to 1, converges to the optimal number. So this is a minimizing sequence. So once I have a minimizing sequence, I have the notion of critical set. So what's the idea is that, well, if I take, I'd like to find my minimal surface as a limit of surfaces in my sequence whose areas are converging to the optimal number, W. So the critical set is just the set of all possible limits where we have to consider the topology of varifolds. Okay, so this is the definition is the following. So the critical set associated to phi I is just the set of all varifolds such that V is a limit, meaning that there exists a subsequence ij a sequence of slices, so some numbers tj in the interval 0, 1, such that the corresponding chain, this would be phi ij evaluated at tj. Well, this is a chain. I consider the associated varifold, and I'm taking all possible limits. And of course, I'd like to just to look at those limits which have optimal mass, so meaning that or maximal mass, if you want, so that the mass of V is equal to W. Okay, so basically, once you have a minimizing sequence, you try to look at all surfaces which have maximal mass and capture all possible limits. So the limits are the elements of the critical set of phi I. And then the challenge is to show that one of these guys is going to be a minimal hypersurface. Okay. I'll just check the time here. 12 minutes. So here's the point where one can ask, I mean, is there a gradient flow, right? Because in the argument of Birkhoff, he had a minimizing sequence, and then he applied Birkhoff's curve shortening flow. And that can also be replaced by parabolic curve shortening flow in the case of Grayson. So here one difficulty is that the natural gradient flow for minimal hypersurface is of course mean curvature flow. But mean curvature flow is still, is still not enough for this kind of setting, for two reasons. First, mean curvature flow is not well defined for chains. And secondly, even if the chain is smooth, you have mean curvature flow, but mean curvature flow have finite time singularities. Okay, so unfortunately, we cannot just apply mean curvature flow at this setting. But there is one flow that works at the level of varifolds, which is still not enough, but it's useful. It's called the pull-tight deformation. The idea is that, remember that I illustrated Mimax with this picture. So I was trying to detect this critical point. So an example of an optimal family that is not pull-tight is something that does something like this. So maybe it goes like this. Maybe there's a point here at the same height. And maybe it goes through x1. Okay, so this is an example of an optimal loop, because the sup of the height function is the optimal number C1. But it's not good because there's another guy with maximum height here that is not a critical point. So an example of a pull-tight loop would be something like this. So the yellow guy is optimal, but is also pull-tight. So pull-tight means that every point of maximum height is a critical point of your function. So the first step in the proof is to deform the minimizer sequence so that it becomes pull-tight. So what's the idea here? This is just something at the level of varifolds. The level of varifolds. Let me draw a picture here. So you take, if this is a picture of the space of noise. So suppose this is a picture of the space of all varifolds with mass, say maybe less than 2 times the width. So varifolds. And inside that space of varifolds, I have a subspace. It's the subspace of stationary varifolds. So these are the varifolds for which the first variation of area is equal to 0 for every choice of vector field. So if you give me a varifold that is not in the stationary set, well, it's not stationary, so this means that I can find, for every v like this, I can find some vector field x, which depends on v. So this is a vector field in my manifold M, such that the first variation of v with respect to this vector field is negative, right? It's not stationary, so the first variation has to be non-zero for some vector field. If it's positive, you consider minus the vector field, it's going to be negative. Okay, so that gives me a direction that decreases the area. And then once you have a direction that decreases the area of v, it's also going to decrease the area of every varifold in a neighborhood. So there's a partition of unity arguments that I won't explain. So there is partition of unity argument. But it's going to give me a deformation H like this. So it's going to be a homotopy of the space of chains, of cycles, that have, say, mass less than 2W in itself. with the following properties. This is going to be continuous in the F metric. And it satisfies the properties that first, if you are stationary, then nothing happens. So the H of T, capital T, is equal to capital T for every little t, if the varifold associated with T is stationary. And the second property is that at the end of my deformation, the mass goes down. So the total mass of this guy is going to be strictly less than the original mass. Unless, of course, T is stationary. Okay? So these are properties which are very similar to Birkhoff's curve shortening flow. So then what you do is, once you have a minimizing sequence, Phi, if I choose a minimizing sequence Phi, I can define another map Phi star, which is just going to be H of 1 Phi. So of course, Phi star is homotopic to Phi, right? So Phi star. Therefore, it's still in the class pi 1. So what happens here is that the sup of the areas is going down because H decreases the area. But it cannot go down strictly because Phi was already a minimizing sequence and nothing can go below W. So this is still a minimizing sequence. But then it's easy to check now, and I leave this as an exercise, is that the extra property that we have is that if I look at the critical set of my new sequence, Phi star, this is going to be contained in the critical set of the original guy, but it's also stationary. So we say in this case that this sequence is pull tight. So every limit of maximum mass is stationary. Okay, so this is good, but not enough. Not enough because, you know, being stationary is still very far from being a minimal hypersurface. So we have to do something extra. I don't think I have time to do it now. So the crucial notion, maybe I will explain this briefly in the afternoon lecture, is this notion of what almost minimizing varifold is. Which is a notion of Pitts. So Pitts proves that for every pull-tight minimizing sequence, there is always a varifold in the critical set that satisfies this property, almost minimizing. And then regularity shows that if you are almost minimizing, you are smooth minimal hypersurface. But I'll leave that for this afternoon's class, okay? So I finish here. Thanks.